away the hours, conversing with the flowers, consulting with the rain. And my head, I'd be scratching while the thoughts were busy hatching. If I only had a brain, I'd unravel every riddle for every individual in trouble or in pain. With the thoughts I'd be thinking, I could be another Lincoln if I only had a brain. Why?
Hi, welcome to Wednesdays with Linda. Sorry for that little glitch there. Today we're going to do part 2 of a presentation that I did last month. Last month we took a look at a private universe, which was a videotape done in the 1980s highlighting misconceptions that students have in astronomy. And we looked at that video, and unfortunately, we went a little bit long and we didn't get a chance to finish that presentation, so this is part 2. If you haven't seen part 1 yet, it's not too late. It's archived on YouTube, and you can go ahead and go take a look at part 1 and then come back and see part 2. Today, we're going to take a look at techniques that you can use in your outreach and your education programs to actually uncover what your audience thinks. And then once you know what they think, what do you do about it? So that's what today's show is going to be about. So just as a very, very, very quick reminder of what we did last time, we took a look at the context in which a private universe was created. That because we're looking at the 1980s when this video was produced, it's important to think about what the 80s were like. The advent of the Walkman, Apple computers brought their first computer to market in 1984, the Macintosh. And then of course there's the Rubik's Cube, but more important, you know, the big hair and everything. But more importantly for education, there was no internet. There was no World Wide Web, which meant that how you got information, you didn't get information immediately, and you got it curated, right? You couldn't just go out, get the information, and make meaning on your own. You maybe had a film strip, or a teacher presented a lecture to you, or you read it in a book. All of it packaged and curated for you. Everything was sort of delivered passively. There wasn't a lot of abilities to interact with information the way you can interact with it now. You can see kids on computers in this screen, and really it was word processing and just basic typing skills. And of course, the Casio, your Casio is always with you, your CAN calculator. That was about as high a technology as you might have in your pocket. We talked a little bit about a very important article that came out in Scientific American in April of 1983. It was the work of Michael McCloskey. Go ahead and go back to that videotape and you can hear much, much more about it. But to get to the short story of this, basically it was unknown what students were actually thinking in a physics class. The assumption was always that students are blank slates waiting to be filled. They have no ideas about Newtonian mechanics or, you know, density or gravity or electricity. They have nothing going on in here at all. And so the lecturer is delivering information by just pouring it into students' heads. Well, what Michael McCloskey found out is that's hardly true at all. And in his case, he was looking at what students thought about projectile motion and forces. And it turned out that the students had ideas that were very medieval. They thought that something moves because it has a memory of the force that caused it to move in the first place. So an idea of a projectile is that when you fire a projectile, there's a lot of force coming from the cannon or coming from the arm. If you're throwing it, throwing a javelin, throwing a ball, there's force. Then when you let go, or when the cannon leaves the barrel, the force ends. So why does it keep moving? Well, according to impetus theory, it was because objects retain a kind of a fluid, a memory of that force that dissipates pretty quickly over time. And as that memory goes away, the ball begins to fall. Well, that's not Newtonian mechanics, but it was the view for quite a long time explaining why things move. Well, why do students have these ideas? Where did they pick up medieval impetus theory? It's a very intuitive idea. It kind of makes sense because we have experiences with things running out, like you run out of gas, or you run out of liquid in a glass. You're used to the idea of running out of something, right? So this is why this kind of makes intuitive sense. It's a lot more sensible than to say when something is in constant motion, there's no force acting on it at all. What? That's not what we see in our everyday life, right? We live in a world of friction. Or to say things will accelerate when there's a force acting on it, and it won't accelerate when there is no force. Not intuitive. So what McCloskey found out is that not only did his students widely possess these ideas, but after he lectured, there wasn't really any difference in what they thought. That didn't change. Even when they got A's on the test, even when they were able to answer his questions correctly, answer the problems, do inclined plane problems, everything was great. You gave them a quiz, they still described impetus theory when describing motions. So this was the first time that anybody really revealed, or at least I should clarify that. There actually was somebody who had done this research about 60 years previous to this. But at least in the 80s, it was sort of a revelation that people came in with these ideas. And they were called misconceptions. Some people didn't like that word, including myself, because it made it sound like people were wrong, that these were bad. They're intuitive ideas and they make sense to the learner, even though they may not match what science believes, right? So we call them private theories. And private theories have lots in common. And it's not just force and motion. They happen in astronomy, they happen in biology, but they're logically derived from somebody's observation and experience. They're not just made up. They're often very similar to the ideas that scientists and philosophers held hundreds, even thousands of years ago. Again, they're derived from observation and experience, and that's how scientists hundreds of years ago, thousands of years ago, made sense of their world as well. A person will hold these ideas for years, even decades, without challenge. They're very resistant to change through instruction, through traditional lectures, reading, videos. They're very resistant to change. Often, these private ideas are way more intuitive than what we would consider the correct answer, what science says is the right answer. And people hold these regardless of their gender, their socioeconomic status, their culture, where they are in the world, their level of education, whether they took a science class or not. Private theories are the same. So I was saying that research on private theories is not new. It actually began with the work of Jean Piaget. And if you've taken any education classes, you've heard about Piaget and who he was. He conducted research on children in the early part of the 20th century. And he used questions, interview questions like, why does the moon seem to change shape? Why is there day and night? He asked these kinds of questions to very young students in addition to others, and then based on their answers, pieced together his theories of learning. So let me give you an idea of some of the questions he asked. Oh, if you want to read more about Piaget, there are tons and tons of books he authored. They're all translated from the French, which he originally wrote in. So for example, he asked, why do we get night and day? And a lot of children said, because the sun orbits around the Earth. Very intuitive, held by scientists and philosophers for millennia. Children also said, it's hotter in the summer because we're closer to the sun, and in the winter it's colder because we're farther away. That was a very common answer among children. Very young children believe the moon is alive because it seems to follow us. When we drive in a car or when we're moving, the moon always seems to follow you, so it must be alive. So they have very animistic views about the planets. So this is what we did. And then we watched a private universe, and I encourage you to go back and do that. And we took a look at what the Harvard-Smithsonian Center for Astrophysics had done as it interviewed faculty and students graduating from Harvard University who had taken tons of science classes, and they asked them about the phases of the moon, and they asked them about the cause of the seasons, and discovered that their answers were absolutely identical and incorrect, absolutely identical to very young children, not young children, middle school children and high school children who hadn't taken any astronomy at all and weren't college graduates. Identical ideas. So we took a look at this film and discovered that people hold all kinds of misunderstandings about astronomy. And a question was raised by one of the people listening: how can I tell what my audience is thinking? So if it's really important for me to know that, so if it's really important to take a look at these children and not see them as blank slates waiting for me to fill them with knowledge, how am I going to tell what these children think if I'm giving a lecture or I'm giving a presentation at a museum or at an assembly? What do? I'm going to give you some examples. And this is a way that you can sort of very quickly figure out what it is your audience knows. Sometimes it's really nice to embed your presentation with some questions for the audience to think about and ways for them to tell you what it is that they're thinking. So this is one I developed when I worked at Harvard, when I was part of the team that helped edit the final stages of a private universe. We then wanted to develop curriculum and activities that teachers could use. So this is one I developed. It's about Kate the astronaut, and there happens to actually be a Kate the astronaut now. There wasn't one in 1986. Her name is Kate Rubins. And in this activity, we're going to say that she weighs 150 pounds on the Earth. 150 pounds. We're going to take Kate to some hypothetical planets, okay? And all I want you to tell me is, will Kate weigh more on these planets, less on these planets, or will she weigh just the same? Now, if you're dealing with an audience, you might want to have paddles or little cards where red is more, white is the same, and blue is less. Now, if this is a class that you actually can spend some time in, because I've told you Kate weighs 150 pounds, you can actually have your audience kind of estimate, well, I think she'd weigh 120. I think she'd weigh 190. So you can actually do numerical things too. But in this case, just more, same, less. Ready? Okay, so here we go. We're going to take Kate on a trip. Her first trip is to the planet Vacuo. And Vacuo is like the Earth in every way. It has the same radius. It orbits its sun in the same with the same distance. It has the same mass, same density. Everything about this planet is the same, but it doesn't have an atmosphere. Okay? So does Kate, who weighs 150 pounds, does she weigh more? Does she weigh the same? Or does she weigh less? So I'm going to give you a minute to think about that. Planet Vacuo. Like the Earth in every possible way, but no atmosphere. More, same, less. All right. I'm not going to put you on the spot, although if you'd like, you can jot down your answer in the chat box and we can take a look and see what you said. That's one way we can do it remotely, or you can type red, white, or blue. But if you do this with an audience and they hold up paddles, you can quickly determine what they believe. You can even sort them together and say, all right, well, I'd like you to form teams of 3 with a red, a white, and a blue tag talking together and arguing about this, because you're obviously in disagreement about more, same, or less, and talk it through and see what you think. So you can actually use these prompts not just as a way for you to figure out what your audience already knows and maybe has trouble with, but you can also use it as a way to get dialogue going. Okay? And that's very important in teaching, in really good teaching. It isn't delivering information the way I'm doing it right now. It isn't lecturing, but it's engaging your audience in a dialogue. All right, should we talk a little bit about what the answer is? Okay, so gravity, a planet's gravity depends on what? It depends on its mass, and it depends on its radius squared in the denominator, right? It's inversely proportional to its radius squared. Does it have anything to do with an atmosphere? No, it doesn't. So Kate weighs the same. Kate weighs the same. Now, I just told you the answer. I wouldn't necessarily do that right away in a presentation. In fact, I wouldn't. I would want to hear discussion. Mainly, I really want to know what people thought when they guessed more, or what they thought when they guessed less. For example, in a lot of the research that we did, we discovered that a lot of people would say less because they said, well, the atmosphere pushes down on Kate. All right, well, that's kind of true, but 14 pounds per square inch, you take away the atmosphere, it's not actually as much as you think. The 14 pounds per square inch that is weighing down on you, you're kind of pushing back out again. So, you know, your body is used to pushing out at 14 pounds per square inch so that you don't implode. So that's kind of a balanced system. So if you think that you weigh less because you don't have that weight of air on you, how much less? It's not much, if anything at all. Let's take Kate somewhere else. This is my favorite planet. It's the planet Styro. And Styro is like the Earth in every way. It has an atmosphere just as far away from the sun. Everything's the same, but it has the density of styrofoam. The density of styrofoam. Much less dense, I'll say, than the Earth is. Okay. Does Kate at 150 pounds weigh more on styro? Is it the red card? Does she weigh just the same on styro, the white card? Or does she weigh much less on styro, which is the blue card? More, same, less. Planet styro. Think about it. What did you come up with? Okay. If styro is like the Earth in every way except that its density is much, much less, that means its mass per volume, the volume's the same, but the mass went down. And gravity depends on mass and is inversely proportional to the radius squared. Didn't change the radius, nothing changed there. We just made the mass much lower. So Kate weighs much less. So it's blue. Much less. Again, if you have an audience and you look around and you see what they said, you can very quickly determine how many people get it. And here's one of my favorites. Oh, and by the way, in case you're wondering what most people thought about that last question about styro, that was really a good test to see how much people understood about the relationship of gravity to the mass and radius of a planet. A lot of people didn't know how to answer that because they didn't know that our gravity depends on Earth's mass. So that's an interesting way to get at that very basic notion that gravity is a force between masses. So now we have planet No-Go. Planet No-Go is like the Earth in every way. It has an atmosphere. It has the same density. Everything's the same, but it doesn't rotate on its axis. It doesn't spin. It rotates around the sun or revolves around the sun, but it doesn't spin on its axis. Everything else is just the same. All right. Does Kate the astronaut weigh more? Red. Does she weigh the same? White. Or does she weigh significantly less? Blue. Planet no-go. Give it a little thought. Okay. You can write in the chat space if you want to make a guess. So here, there's nothing about the gravitational force between yourself and a planet that depends on whether the planet spins or not. Doesn't matter. So here, Kate the astronaut weighs just the same again. But let me tell you a little bit about what people thought. There are a lot of people that thought if a planet doesn't spin, it doesn't generate a gravitational field. A lot of people thought that. And you might find that true in adults, children. There's something about spinning, people think, that makes a planet have gravity. So a lot of people said less, or she'd weigh nothing at all. She'd be weightless. Other people said if she doesn't spin, then the planet doesn't push her off her feet, doesn't swing her off the way it apparently does on Earth, which it doesn't. So some people would say less. There's something about rotation that people think is pretty magical. So another person I know in an interview I did said, well, if the planet doesn't spin, it might not have a magnetic field. And if a planet doesn't have a magnetic field, it doesn't have a gravitational field either. Something mixed up there, that if you have a magnetic field, you have a gravitational field, that somehow those are linked. No. So that's just one example. And why would you use a question like this? Well, let's imagine you're going to talk about black holes. Everybody wants to know about black holes. And you're going to you're going to tell them all about how black holes have their mass compacted in a tiny radius, and that's what makes the gravitational force, strong as you get closer. Well, if your audience doesn't really have any understanding, or is having a lot of misunderstandings about gravity, that's going to be a very, very hard sell. So I might want to do an activity like this before I start talking about black holes. Maybe you're talking about orbits. Maybe you're trying to explain how the slingshot effect is used, or you're talking about using gravitation to figure out escape velocity. Again, if there are misunderstandings like this about gravity, it might be a difficult concept. So you might want to start with Kate the astronaut. Or you're just teaching about gravity. In any case, it's a really nice activity, and it's quite illuminating for you, and it's also illuminating, for your audience. So here's the $64,000 question. Now that you know what your audience knows and is thinking, what are you going to do about it? What if you discovered that half your audience has some serious misunderstandings, some serious private theories about the topic you're about to go into? What do? So I'm going to have you watch this film. Basically, what you've just done with your paddles is something that's done electronically in a lot of classrooms today. And maybe you've been in a classroom that uses it. It's called clickers, where students are literally given electronic devices that have a red, a white, a blue button, sometimes more choices, A, B, C, D, E, F, and they can log their guesses onto their electronic devices, which immediately goes to the instructor in the front of the room and is graphed so that everybody in the class can see what everybody is thinking. This is a more sophisticated way of doing what we just did with the paddles, but I'd like you to take a look at this film and see how discovering what your audience thinks and knows and having them discuss with each other can be an extremely powerful way to teach. So enjoy this.
Getting your students to talk to each other about the things they're learning can completely change the atmosphere in your classroom. Tools like these clickers can help get your students excited and engaged like you've never seen before.
I love clickers.
I definitely feel more involved when a class uses clickers.
But this isn't automatic. Clickers won't promote class participation on their own. In this video, we take a closer look at how an instructor can use a clicker effectively. You might be wondering, how do you write a good, challenging, and conceptual question? A question that will spur peer discussion. Then, how long do you let students chat before stopping the vote? How do we go about guiding students to understand the rationale behind an answer? And then what? How do we use this information to help guide our teaching? We're going to zoom in on each of these steps in this video. After all, it's not the clickers themselves, it's the how and why they're used that makes them effective. First and foremost, don't leave your students in the dark as to why you're using clickers.
The most important thing for a successful experience for both the students and the instructor is that everybody should buy into it.
So if you want your students to hate your use of clickers, fail to explain that it's a device to improve learning. They will assume it's a device to track them or to test them, and they will resent that.
Okay, but how do you use clickers to help your students learn? The best questions aren't about simple recall. They're challenging and conceptual, and they'll help drive the lecture.
I think the greatest challenge for the instructor is to write meaningful questions.
There's a tendency to use questions which are not challenging enough. Maybe that's because we all feel good when 80% of the students give the right answer.
My personal philosophy is the higher the level at which you challenge the students, they will rise to the occasion.
It seems to make the class hook together much more nicely when the clicker questions are part of the lecture rather than, I'm done with something, let's see if you got it. It's not a quiz, it's part of the class.
Clicker questions aren't helpful when I'm just repeating what the teacher has just given me. I like to have the questions progress the class rather than just a regurgitation of what I've been told.
The best questions that I have to ask for peer discussion are questions that have come from the students themselves.
That's really where you want to zoom the clickers in on. Something where it's not trivial, it's not memorization, it's an idea that they're struggling with.
Well-formulated clicker question should make you think, and it should make you address the concept at hand, but it shouldn't be too tedious or laughably simple, because that's just a waste of time.
The power of clickers is that they can get students to articulate their reasoning, which in turn can help them make sense of the material.
I think I learn better when I talk to other people around me. There's something about debating and in a sense teaching other people when you think you've got the right answer, or learning from other people when they've got the right answer, that's really helpful in that learning process.
Students are learning more and more deeply when they're figuring things out for themselves.
But what if students are reluctant to talk to each other? Many students aren't used to participating in class, and you may have to show them that you're serious about this process. I often wander around my lecture halls, listening to student ideas and asking questions. I let students know that this is what we do in class: discuss and debate ideas. Having your students talk to each other doesn't just help them learn, it also helps you as an instructor to see how they're thinking about the material.
And I was never able to see inside my students' heads before. Peer discussion and clickers make your students' reasoning accessible to you.
Gas and dust. To me, those signal new stars.
Now you've got them all talking. So what do you do during this time?
One of the initial barriers to being comfortable with peer instruction is the strange feeling of standing in front of a classroom and not saying anything.
I think circulating around the class and listening to what's going on can help you feel that, yes, they are on topic and you haven't really given over the class. It's a different way of the students learning the information.
So giving students the chance to talk to each other helps them learn and gives you the opportunity to see how they're really thinking. Now you've got the room buzzing with debate. How long do you let them talk?
So with the system that we're using, we get a count of how many students have clicked in. And so typically when approximately 3/4 of the class is clicked in, to me that's a sort of a signal to start wrapping things up. And I'll sort of say, well, let's wrap this one up. So let's pull this together and have a little discussion.
Typically, it's best to allow between 2 and 5 minutes for student discussion.
Sometimes it's the noise level in the room has gone down and it's clear the conversation is over. They have nothing left to say to each other and I might as well end it.
All right, the results are in. So how do you go about talking with the whole class about the question?
I think the more a teacher will facilitate conversation after the clicker question is ended, the more effective it is.
After all the votes are in for a clicker question, I really like it when professors ask people to defend certain answers. So they don't reveal what people voted on yet, and they don't say the right answer. It's really useful because you get to follow the thought process all the way through.
I might say to the class, so irrespective of whether you voted this, I would like to know why you think somebody might reasonably vote E. And this has changed what it means to respond. It doesn't mean you believe it. It means that you're actually a good student for coming up with an incorrect reason.
The best part, I think, is when they go over why the wrong answers are wrong. You know, you think it's answer A, and you really think that that's why, you know, you've got a reason why you chose answer A. And they're like, okay, well, answer is C, moving on. You're like, well, I don't understand why my answer was wrong. One of the best ways to learn is making a mistake or doing the wrong thing and learning why it was wrong.
But what about the histogram of student responses?
For the students, I think what is most rewarding is the feedback that they receive when the histogram is projected in real time.
But when do you show this to the students? This prompt feedback helps students learn from their mistakes. But you can choose whether to show the histograms to the students immediately or to wait until after you talk about the question. This is an important part of the clicker question, and it depends on how the students voted.
So when I have the histogram, there's many different outcomes, and the most common one is it's 90% correct.
In this case, there are pros and cons to showing the histogram before having a whole class discussion. Either way, it's important to discuss the answer before moving on.
Let's take a look at this. So there's a pretty strong agreement on E, none of the above, but I got some B's and C's. B is very tempting. I like the B. What's wrong with B? Pardon? It's not you, it's big R. It's just notational convention.
As I've talked to students, they always come back and tell me they appreciate the fact that we still talk about the correct process even when over 90% of the students got the right answer. And I think that's important for instructors to know.
What if about 70% of the students got it right? What might you do then?
If it's 70-30, you know, you look at that histogram and you sort of think, oh, they all got it, but they sure as heck didn't. A third of the class did not get that question. That would probably be a time when I might not show the histogram. Keeping it hidden allows you to say, who can tell me a reason for B? And if you're voting B and it's wrong, you don't know that you're in the minority yet, and so you might get that voice.
So the histogram is particularly important when the student votes are not unanimous. Sometimes the class will be really divided on a question.
There is a mixed vote.
Showing the histogram here can be really powerful, as long as you don't take the first right answer and move on.
If it's 50-50, it's brilliant. You show the histogram because that gets everybody excited. Now there's a debate in the room and we have to resolve it. And I try very hard not to be the resolver. So if it's 50-50, we got to hear voices and we got to let the students decide.
So I'll typically call on someone who gave a wrong answer and let them speak first, and then call on someone who gave a correct answer and let them articulate their reasoning, and then maybe turn to the class and say, so what do you think about these two arguments? And then I'll wrap the whole discussion up myself and say, this is the reason I favor the correct answer. Center of the Milky Way, and that's a good analogy because it is.
So you'll have very different kinds of wrap-up discussion depending on how the students voted. Then what? Clicker questions give valuable feedback to you and your students.
What I like most is that it gives me a chance to think about what I know and test myself, independent of everybody else in the class.
I think the most powerful thing about using clickers in the classroom is the ability to instantly get feedback about what the students are thinking about the material and whether they're grasping the material.
Great, but then what? It may be tempting to use clickers as a quick check to see if your students are on board and simply continue with your plans for the day. But they're not just a quiz. They can help you determine how you might continue with your lecture.
When the histogram comes up and I do see a large variation or even the majority choosing the wrong answer, it lets me know that I'm not the only one that's not getting it. It lets the teacher know maybe I need to change my approach.
That's one reason why it's important to make the clickers count only as a trivial amount of the student's grade. That helps the students take them seriously, but not stress about getting the right answer.
Use the clickers regularly. and use them in such a way that people really have to talk about it.
Don't ever take for granted that your students learned it the first time you presented it. Students need for us to go back and review concepts, to integrate it, put it in context, and the more we engage them as learners, I think they are also active participants in the process, which is what we all want.
Using clickers well will take some practice, but it's worth it. Be patient with yourself as you learn to use this new tool.
I hope you enjoyed that. I think what this particular video demonstrates is not just how to use this electronic tool, but the whole notion of the power of having students in the class articulate what they know so that you understand it, and have real vigorous debate about ideas in class. Because let's face it, we don't really learn things simply because somebody has poured the information in our heads. We learn best when we're faced with a real challenge to our beliefs, and a challenge that we have to, argue for, right? That we have to really stand up for. And if you're surrounded by people with different ideas, and the give and take of that kind of discussion can be a really powerful way to really change ideas, right? To really transform how you think. Simply talking about it and lecturing is not going to be enough. So when you do your outreach, your presentations, your teaching, give this method a lot of thought, because if it's really about teaching the students that are in front of you, this is a very effective way. I want to end with a quote from Piaget, which I think is really important to think about, particularly after you've seen the film about clickers and the power of having students share their ideas. He said, "The principal goal of education in the schools should be creating men and women who are capable of doing new things, not simply repeating what other generations have done. Men and women who are creative, inventive, and discoverers, who can be critical and verify and not accept everything that they are offered." So keep that in mind. I think that's very sage advice. If you'd like some more information about what we talked about today, this is the original film that we saw last month, A Private Universe, and you can view that film and get additional resources and other films in the series in the URL. If you'd like to know more about Jean Piaget and his theories, there's a URL you can visit. And if you want to know more about clickers in the classroom and see other videos from the same group, you can check out this third URL right here. All right. Well, that brings an end to another episode of Wednesdays with Linda. I look forward to seeing you in a month, when we'll talk about some new aspect, another aspect of education and astronomy. And maybe we'll do an activity next week so I don't lecture so much. Bye-bye.